Gina, I'm so stressed. Look at this vector problem. How do you find the angle?
Noah, you need to do some yoga and meditation to de-stress.
Thanks so much, Gina. This really helped.
Did you know that there are actually vectors in yoga?
Vectors in yoga.
The first important concept to understand is equilibrium and balance. The goal of equilibrium is to have a net force, the sum of all forces, to equal 0. The forces must be balanced, there can be no change, the object keeps doing what it is already doing, and nothing starting or stopping the object.
There are two different types of equilibrium. Static equilibrium is when an object is at rest and is going to stay at rest. And dynamic equilibrium is an object in motion at a constant velocity, which is speed and direction, and a vector quantity. In yoga, most of the time, we're in static equilibrium.
The next key concept to understand are forces. One force is the gravitational force. This gravitational force states that objects fall down when they are not supported, because gravity pulls them down.
The next force is normal force. This force is the support force, which is perpendicular to the surface.
Another force is tension. Tension is a property of the situation, a string, rope, cable, or an arm that is pulled taut.
The next force is friction. Are two surfaces touching? If they are, then the force of friction is at work.
Our last force is torque. Torque is a force applied when objects twist or rotate.
We don't want torque in most poses in yoga. For example, if Noah's in tree pose and I push her over, there will be torque because Noah will twist and fall. Another yoga pose where the goal is to have no torque is mountain pose. In mountain pose, you're in static equilibrium, or complete balance. The forces at work here are normal force, gravitational force, and as I said, no torque.
So now we are going to be doing an FBD for our mountain pose. An FBD is a free body diagram. So first, we are going to draw a little dot. This is mountain pose. How do we know it's mountain pose? Because we're going to label it mountain pose. So as we said before, there are two forces acting on this pose. There's the gravitational force, which is going to be mg, which is the mass times gravity, and that points downwards because gravity is always pulling you down. Then we've got normal force, which counteracts gravity. So now we need to solve for the F net. So F net is going to have to equal 0 because this is in static equilibrium. So how we solve for the F net? We are going to be doing force normal minus mg. So let's put some numbers to this. So let's say our person weighs 31 kilograms, okay? And gravity is 9.81. So, 9.81 newtons specifically. So how would we do this? We would do 31 times 9.81. So, 31 times 9.81 minus 31 times 9.81, since gravity and the normal force are equal, would very clearly equal 0.
The next pose we're going to look at is meditation pose. In meditation pose, we're again in static equilibrium, where the goal is complete balance of the mind and body, because this is yoga. The forces at work here are torque, gravitational force, and tensions. As you can see in the diagram of the yogi in meditation pose, the tension at work here is the force of the deltoid on the humerus and the force of the scapula on the humerus. At this point in the project, you're probably thinking, wow, this is a great physics and anatomy project, but where's the trig? But if we consider the musculoskeletal system of the upper arm as a right triangle, we use basic trig applications to show that this problem is in equilibrium. The F net of all four forces cancels each other out, showing that this is an equilibrium problem. Using our trig labels, the hypotenuse is the deltoid muscle, or the force of the deltoid on the humerus. The base is the humerus bone, or the force of the scapula on the humerus. The height is the scapula. The red arrows in the diagram represent the directions of the forces. You can see this by the fact that the gravitational force is pointing down. The gravitational force is mass times gravity. Theta, in the specific problem we're going to be showing you, is 17 degrees.
As we were saying before, we are now going to show you how to solve this problem. So, as we can see here, we've got the gravitational force. We have theta, which is 17, as we said before. We have the scapula right here. This is the force of the scapula on the humerus. This is the force of the deltoid on the humerus. And we're also going to have torque around point P. So now, I'm going to show you how to solve this problem. So what you need to do first is you need to tally all the forces in the x direction and set it equal to 0. So in the x direction, we are going to have the force of the deltoid on the humerus, cosine theta, minus the force of the scapula on the humerus in the x direction. The force of the scapula on the humerus goes in two directions. Now in the y direction, we are going to have the force of the deltoid on the humerus, sine theta, plus the force of the scapula on the humerus in the y direction, minus mg, which is going to equal 0. This is also going to equal 0. Now we are going to pick a pivot point with lots of mystery forces going straight through. I'd say our best pivot point's about here. We have a lot of mystery forces going through this point. So now, in order for us to solve for the x and y that we were discussing before, we are going to need to solve for torque. So mg half L minus the force of the deltoid on the humerus, sine theta L2 equals 0. So now let's crunch some numbers in. So since our mass in this is 3.6, we're going to do 3.6 times 9.81, which is going to equal 35.3. Okay, so we are going to have 35.3.5 L, and as we can see, L here is going to equal 0.66 meters, which is how long the humerus bone is, minus the force of the deltoid on the humerus, which we don't know. We are actually solving for that in this equation. Sine of 17, L2, which we know from this equation, is going to be 0.15 times 0.15. And that's going to equal 0. So the sine of 17 times 0.15, which is going to equal 0.04385, which is going to equal 0. So now, let's move the 11.649 on the other side. So we're going to do negative 11.649 equals negative FDH 0.04385, divide. So we're going to divide this by this. So 11 points divided by 0. We are going to have an FDH to equal 266. Now we're going to take that FDH and we're going to put it in our original problem to solve for the x and the y. So now, if we remember, we are going to put this, we're going to do, for x, we're going to do FDH cosine theta minus FSH x equals 0. Remember, this is the deltoid on the humerus, and this is the scapula on the humerus in the x direction. So now we know that this has to be 266 cosine 17 minus the F scapula on the humerus, x equals 0. So now we're just going to do 266 cosine of 17, and now we're going to have an FSH in the x direction to equal negative 254, or positive in this case. Now we are going to solve for the y direction. So y is going to be FDH sine theta plus the FSH in the y direction minus mg to equal 0, as we had before. Do you guys recognize that this is vector addition? Because we are using these vectors to solve for our force. So now, FDH, we obviously know our old friend 266 sine 17 plus FSH in the y direction minus 35.3 equals 0. So, as we remember from before, 266 sine 17 is going to equal 254 plus F scapula humerus, y direction, minus 35.3 equals 0. Now we are going to add these two together. 77.8, let's round. minus 35.3 is going to get us to 77.8. Is going to equal 42.5. So now we're going to move negative 42.5 is going to equal F scapula on the humerus Y. See that? All right. Now we are going to we're going to solve for the torque around the point P as we said before. And FDH. This is when we're going to see that our forces cancel out. Are you guys ready? This is the moment of truth. Okay. FDH is going to equal MGL over 2L2 sine theta. And this number, we want it to equal 266. But we're not going to put 266 in. So 35.3 times 0.66 over 2 times 0.15 sine of 17. Are you guys ready? Moment of truth. Will this equal it? So 35.3 times 0.66. Okay. 2 times 0.15 sine of 17. I'll show you guys what I'm doing. So now we're going to divide these two by each other. You guys ready? Ho ho! 266! So we know that this is right. Yay! Now, let's do the y direction of the force of the scapula on the humerus. So, F scapula humerus, y direction, equals mg minus mg times L over 2L squared. So this is going to have, now we are going to do the force of the scapula on the humerus in the x direction, which is going to equal mgl to L2 cotangent 17, which this is going to have to equal 254. Do you think we can do it, Dina?
I think we can.
All right, let's do it. 35.3 times our old friend 0.66 over 2 times 0.15 cotangent 17. So as we remember from before, this is going to equal 77.6 times oh, whoops, sorry everyone. I want to go cotangent of, all right, I'm scared. Oh, 254. Everyone see that? So all the forces cancel out. Do we see that? Because they all equal each other. Because in the x direction and the y direction, these are going to also equal the torque in the x direction and the y direction. So in total, with our four forces, we are going to have a happy equilibrium.
So now you're wondering, why is all this math relevant? Well, it explains the importance of balance and equilibrium in different yoga poses. If you're doing meditation pose or tree pose and you're tipping over, that means that you're not in equilibrium. Our sources were Miss Eliezer, and Miss Eliezer. Thanks for watching!